Hello, fellow. My name is James Owusu-Appiah, and I believe in innovation and doing things differently. This video has been prepared for you to guide you through some well-known concepts that will aid your studies and preparations towards exam. Due to COVID, we cannot meet in person to discuss, so I hope this video finds you well and helps you achieve excellence. Thank you.
So we have to flip things around again. I'm done with that, and let me just insert it here. Okay, into our schematic, and then you can see. Let me do that again. We have connected our input. We have connected our room to our circuit now. It's now part of it. Next is let's go and continue with our transpiling process, or the generation of the room image. So yeah, I said we'll be using Sequence. Now this Sequence is a program that I actually wrote, and as such is, and so like I will kind of give you the banners and things that you can use it, because you won't find it anywhere else. Let me I will so these banners will be available to you. Yeah, but currently I don't have a Windows version for it yet, but I'm sure by then there'll be a Windows folder here, so that you can have the Windows binary too. So to kind of use it, I already have it installed on my system, but for you, what you need to do is that you just copy that binary to this, to the folder where, because this file, right? We save it here. This CPU instruction, the second, this file is here, right? So this is a file I want to compile or transpile or generate the room from. So I'll just paste that second, this thing here, the binary here, and you can just, so for Windows will be like second.exe, but here just type second if you're on Linux, and then just then what the file, the text file, CPU instruction.sequence. So this is a second file, and I want to take note of this. As we run the command, it's going to generate the room. So you can see that. So you see, I generated this room image. So if there is an error, it will let you know if there was an error in the script. But if there's no error, you should see the final image, this thing be generated. So if you open the content of this, you see that basically what they wrote here is just the content of, it's a completed table, right? Because you know that our 10-bit input has about 2 raised to the power 10 possible states, right? So if you check these things, this 2 raised to the power 10, and so 2 raised to the power 10 should be something like this, in that range. So there is something, you should get it. So that is 1024 actually. And so these are the possible state it wrote, and then it will to auto complete the table and then do all those stuff for us. So once this file has been generated, that's all we need. So we just have to go to Logisim and then go to edit content, right? Edit content. Don't go to load image. So assume you never had an image loader, all you have to do is to come to here and then open, and then you see CPU image, right? Transfer to where you save it, and then you just click on it and it will get loaded, right? So once it's loaded, you can close this window and you have it here now. So your room has been about programmed, right? It now contains your truth table. So your truth table is now loaded into the room, and with that, which means we are done with our, generating the control unit for our jam instruction so far. Okay. And there's one thing to, actually there's an error here which we might not have taken notice of, but let me try and correct that to you. Because you see, at this instant, that's where the jam instruction begin visible to us. So here, instead of it being X, it should be jammed. So if you maintain this X, now it didn't cause an issue because it's in the jam, so we were not affected. But if you maintain this here, it will cause a problem for your script later on. So it should be 001. So all here should be so copy this thing here up to, on this thing, because now we have the instruction with us now, so we don't have to say we don't care about the state. It's a jam instruction we're executing. So is jammed. So this is important. So yeah, so that is the correction to make, and it will be the same thing. We'll have no effect because it's only jam that we have so far. It will have no effect on our final circuit. So I will save that, just make the changes. Now next, once you have done this, next needs to test to make sure that your control unit does what it said it should do here. So which means at every state the signal sent its output, it should correspond to what your table says it should do. So that's how we're coming to verify that. So let's start. Let me Control R to reset everything so that the micro instruction counter is now at 0. And now see at step 0, right, when the micro instruction counter is at 0, see the signal that we have at high. Does it correspond to what is on our table? So let's see. We have program counter output enable high. We have instruction memory address register. So make sure that the signal that our control unit is outputting at step 001 should correspond to what our table says. So we have the signal high, IMOE high, CIRE high. So let's see if those same signal matches what we have here. So here we check here, we have CIRE high, then we are at step 001. So let's see, then IMOE is high, and this is also high. So yeah, we have these three signals high. IMIE, this is high, this CIRE IE is high, and then okay, I think these are the only two signals that we have higher, IMOE and CIRE. So let's compare that. So you can see IMOE is high, CIRE, this is high. So it does what we expect it to do at what step 001. So let's execute this instruction manually. So I will click here the rising edge of the clock. We expect that what is here now should be copying to what is here. So you use watch the change. You can see that what the 001 hours here, this content here will copy here. So on the falling edge, this will increment to the next count. So you see it go to 010. So at step 010, we have only one signal is high. That's the program counter count enable, right? So if you come back to the table here, you see at step 010, right? So at step, this is step 010. So only one signal we set high. So yeah, and let me just adjust a little bit. It's always good to kind of keep your table in line, because if it's not this, you have some issue. Like it's not very important, but they help you to kind of keep your table content in line so that it make it clear. I don't know how come these things got displaced, but keep track of that these signals here 011. So this is high, program counter here the program counter output is enabled, and then this is also high. So it's fine, the signal corresponds to what we expect. So on the rising edge of the clock, we expect that should be done. So the content of the program counter should be what loaded into here. So on the rising edge, you can see that value got loaded into the register here. So on the next falling edge, we should go to our step 4. That is step 100. Step 100. So at step 100, what do you see here? We have, what other signal do you have active here? So step 100, the signals we have here, there was program counter load enable, and then this output enable. So that is a signal that we have here. This is high, and then program counter load enable is high. So it's fine. So on the rising edge, that should be done, and on the falling edge, we expect to go to step what? 11. We expect to go to step 101. But unfortunately, because the operation at step 101 is an asynchronous operation, so this is only one, and here this is asynchronous, so you will never see the counter go there. You never see the micro instruction counter reach. You won't see it. So on the falling edge, it will go back to 0 because that has been done. It cleared the micro instruction counter to 0. So that's why you don't see step 101, but it will execute perfectly. So with this, you can see that we have actually done with our with our jump instruction that way. So if you see in the first way, the program that rotates a jump program, right, using the code for our jump is this, the opcode 000, and this is a location I wanted to jump to. So we say we wanted to jump to location what 10 is A, so in 10, this location, right? And if you come to this location, see that there's another jump instruction saying that we should jump back to what 00. So basically, at the end of the day, you have a loop, just looping. So it's the same jump instruction, but let's just see how the program. Let's just continue to go execute the next instruction and see. So we are at 00 and T. These things have been set up. The C instruction here, the program counter output the number side, and this is ready. So on the rising edge, that should be copied here. So you see this got copied here, right, to fetch this operand, right? Then on the next falling edge, the next instruction set of instructions should be set up. This is high, and then this is what high. So this is going to be loaded into what this, right? So on the rising edge, you see that happened, but you didn't see the change, but because of that. Then now we increment the program counter so that we can fetch the operand or location. So on the rising edge, that got incremented. On the falling edge, it outputted to the bus. On the rising edge, it gets loaded here so that you can see we're now at the operand, where the operand is. On the next falling edge, the instructions are also set up again. This is on a is now on a bus, and then next this is ready to be loaded into it. So on the rising edge, you see that 00 get loaded into a program counter. So and just like that too, and just like that we are done again. So let me just toggle the clock, similar, so you can increase your clock frequency, but I'll run it at 2 Hz so that you can see now. So just watch how the program executes now that everything is done. So basically this is how things will be like. I mean, all your other instructions, just look at how this instruction has been implemented, right? I could have tried to implement the rest of the instructions, but you try and look at them. These are the rest, some of our instructions that we initially stated. So you have to load this thing, but these are just moving data. They are just similar to what I did there. So you think about it and see how you implement these things, right? If you have some challenge, maybe later I might work on something like this, but try and do this thing and see. So you can see the program that we have running, just a loop. It will keep on looping like that, but see how it works. And these materials and things will be available along with the video, so you can kind of go through it and see how this thing, systematically how it works, and then how we are able to generate the control